Algebra 2 honors students, this is going to be the next part of our stats unit, day 6. Let me turn on the camera here. And these are the notes. By the way, kind of disregard the fact that it says unit 15, day 6. This is an old unit 15. So therefore, it's going to be labeled a little bit wrong for the next couple of lessons in this unit. But we're still in unit 18. This is, in fact, the day 6 lesson on sampling distributions. And one quick thing I'll note is that this lesson probably by the end will be pretty short when all is said and done, because we were going to try to simulate and help understand sampling distributions a little bit better today. If we were in class, I probably actually would have given you all a bag with 10 colored chips in them. So what I mean by that is not like potato chips, but kind of like these kind of type things here. And what was going to happen is you would have simulated picking one chip at a time from that group of 10, and you would note what color it was and then put it back in and then repeat that process again for a total of 10 trials. So what we're going to say at the top here is that the population is that we have 10 chips in a container. Okay, so like I said, you would pick one chip out, you would kind of note what color it was, and then you would go from there. And if I asked randomly from the crowd for some different samples of what happened, I'll tell you what we're going to be looking for is specifically red chips. Okay, so you're going to do this 10 times. You're going to record how many of the chips that you got were red, and I'll tell you that I did this. And these sample statistics, these proportions that we're looking at of how many red chips we got out of the 10, would be called a P with a little kind of hat over it. So it's actually known as P hat. Okay. So trial 1, I'll tell you that my P hat was 1 out of 10. Okay, I picked 10 chips out of the bag, picked one up, put one back, picked one up, put it back in. And at the end, one of the chips was red out of the 10 total attempts that I made in trial 1. For trial 2, my P hat was 2/10. Okay, so that time I got 2 red chips. For trial 3, P hat was 3/10. And for trial 4, P hat was back to 1/10 again. So think about, the fact that, okay, if I only did this trial 4 times, what if we did the trial 100 times? What would that help us to determine in the end in terms of the proportion of red chips that are actually in this container? So I haven't even told you what was really in the container to start with. This would be known as the population characteristic for these proportions, which will just be known as P. Okay, so P is the actual population of red chips, that proportion that are in there. The actual population was 2 out of 10, which would be 0.20. So what we're going to wind up doing is we're going to think about, okay, well, if I take a look at these 4 trials of choosing those 10 chips and recording how many of my 10 were red, what would be the average of all these? Okay, so this would be what, 0.10, 0.20, 0.30, and back to 0.10. If you add these up quick and then divide by 4, I'll tell you that the average of your P hats winds up being 0.175. So about 17.5% of the time, we wind up getting red chips from our 4 trials. Now, if there were 30 of you in class and I recorded all 30 trials, what do you think is going to happen to this average? And I'm hoping what you're shouting out from the comforts of your own home is that this average, if we look at all the trials from every single person in our class, is going to start to get really, really, really close to what the actual proportion was of red chips that are in the container, that population characteristic. So that's what we're going to actually start talking about in the conclusion section here. So in conclusion, let me just kind of pull this over here. Okay. what we just did was a sampling distribution. Okay, all those different trials wound up creating what are called a sampling distribution. And the mean of lots of sample statistics, that's what I calculated up here, the mean of all those p-hats is approximately the population characteristic, which is the actual percent, that actual proportion of red chips that happen to be in the container. So will it be exact? Most likely not, but it's a pretty darn close approximation. And you can imagine that, like I said, if we had done more than 4 trials here, if I had 30 students, that this percentage probably would have been even closer to 20% if I averaged all 30 trials. Symbolically, what that's going to look like is we know that mu represents the mean. Okay, so the mean, or the average of all the p-hats, is going to eventually equal that population characteristic. Okay. All right, moving on from there, if we draw more for each trial, so we increase the sample size. We had a sample size of 10 just a moment ago. Do you think the proportions will be closer together or more spread out? Let's try drawing 3 more additional trials. So then I would have tried having you guys consider n equals 20. So if we increase that sample, if we choose, a chip 20 different times and we record how many of them are red, what do you think would happen in that case? Is it going to be a better representation of what P is, or is it going to be, not as great of a representation? Well, I'm hoping that you would consider that the average of your p-hats should now get even closer to what P is. Okay, so if we increase the number of trials, that's going to get us even closer to what that population characteristic is. And what that brings us into is our next conclusion here, is that as the number of trials n increases for your sample size, okay, not necessarily number of trials, I should say, but the number of times we're choosing a chip here. So we went from 10 chips to now 20 chips. The variability, which is how far spread out the data, is going to decrease. And that would be the goal. Okay, so the larger the sample size here, variability goes down. And that measure of how far spread out the data is, I'm hoping you're remembering that that would be a measure of standard deviation. So symbolically, what we're looking at here is as n increases, the standard deviation sigma of your p-hats should decrease. Okay, that measure of spread in the data. We're going to analyze some cases where we can actually, without drawing chips, one at a time and doing some recording, as fun as that could be, we're going to do a little bit of simulation using the calculator. So if you have a calculator, go ahead and take that out. On the next page, it says we can actually save time by simulating the scenario using the GC. We're going to use a population proportion of 40% for selecting red this time. We'll simulate the sample size of 20, which means we're going to draw 20, and we're going to record how many reds we get. So what we're going to do is we're going to generate a list of random numbers on the calculator. And there's a lot of different ways you can do this, but 40%, I think a lot of us might think of it in terms of that if we have the numbers 1 through 100, 1 through 40 would represent a red chip being pulled out, and 41 through 100, it didn't say anything about blue, but we'll just, why don't we go with some good old Fairport colors? We'll say that the other 60% are blue, even though it didn't say that. How are we going to get the calculator to do this? Here are the kind of keystrokes here. It's math, and then over to probability. Option 5 is generating some random integers. The notation for the older operating system, which I know some of you still might have, and then a lot of us, I think, will have the newer operating system. So let me show you how this is going to work. So if you go to just math, sorry. I was thinking about normal CDF for a second there. All right, hit math, and then you'll see at the top here, it says probability. So you're going to go over to probability, and then you'll notice option 5 is that option for rand int. So choose 5. And the lower that we're going to look at is going to be a value of 1. The upper value is 100. And the value of n is we want to get 20 random numbers from 1 to 100. So choose n to be 20. Hit enter. It will paste it now on the home screen. And if you hit enter, it is going to give you a list of 20 numbers somewhere from 1 to 100, which is perfect. And if you scroll to the right, you're going to see more numbers. And if you scroll back to the left, you can kind of see where you started with, okay? But I think the best thing to do with that information is actually store it in a list on the calculator. So you can do that by saying, okay, once you have that typed in, if you hit the key down here that says stow, which maybe we've used that a little bit. I think we used it in that crazy mortgage payment formula. If you hit stow, you'll see that it says take your answer and put it into, I want to put it in list 1. So how do I get list 1? Second 1. So it's going to say store that in list 1, hit enter. So now it's just showing that same list again. Here's the list. If you now hit stat and then hit enter for edit, your list 1 should have those random digits. So what I would like to record is how many of those are between 1 and 40. How many are red? So an easy way to do this would be, I guess I could just scroll through the list. But there's one last function that I want to show you that I think is pretty cool that will help me to more easily and I guess a faster way of identifying how many of the numbers are between 1 and 40. So if I actually just hit stat again, option 2 says sort A. And what that means is if you hit option 2 for sort A, you can sort that list and it's going to do it in ascending order from least to greatest. Sort D, which was the other option, would sort it in descending order if you wanted to do that. So sort A for list 1, again, that was second 1. Hit enter, it says that it's done, and you're going to be wowed and amazed when you go back to stat and then hit edit, that list is now sorted from least to greatest. So let me count up real quickly here how many of these were between 1 and 40. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, the next one is 41, so that's not what I'm looking for. But that 38 right there, that is the 9th number in the list. So my first p-hat, my first trial, gave me a proportion of 9 out of 20. Now, 9 out of 20 should be is 0.45. Remember what the actual percent of red is 40%, so that's pretty close. Okay. Let's try this a couple more times. So you go ahead on your calculator, try it a few more times, see what your p-hats wind up being. Let's see how quickly I can do this. Actually, if you go back to the home screen, you can go up and highlight that rand int that we did. You don't have to retype that in all over again. Hit enter again, and notice how it gave me a new list of values. I'll maybe get fancy and store this in list 2. Why not? So store second 2 is list 2. And while I'm at it, I'll sort list 2. So stat option 2 for sort A for list 2 done. If I now go to stat edit, I can see the numbers in list 2. All right, how many of those are between 1 and 40? Not as many this time. Actually, we stopped at 7. Because then the next number after that is 51. So we got 7 out of 20 the second time around. And you can either follow along with me or try your own trials, see what winds up happening. 7 out of 20 would be 0.35. All right, let's try another trial here. So let's quit this. Copy the rand int again. There's that list. Let's store it in list 3 while we got it. Okay, and then I'm going to stat sort A for list 3. Check out that list. And up till we can include 40. Okay, 1 through 40 were the numbers we're looking at. This is also another proportion of 7 out of 20. So that's 0.35. And then finally, our last sample, we'll do one more time. Quit here. Oops. All right, we got to do the rand int again. One more time. Store it in. Why not? Let's do list 4. We'll do a quick sort on list 4. And stat edits, list 4 up through 40. Boy, a lot of 7 out of 20s. Huh. Okay. So I got 7 out of 20. One more time, which we know is 0.35. So the idea here would now be to average those sample proportions right there, those p-hats, and this total thing was called a sampling now distribution because we've done multiple trials. Okay, and if I take the average of the p-hats, in this case, let's see what we wind up getting. So clear this out. 0.45 plus, we had 3.35s, right? And then if I divide that by 4, we got that the mean of our p-hats is 0.375. And we know that the actual p in this case is 0.40. So that's actually pretty close, even though we only did 4 trials, right? So how could we get even closer? We could do more trials, find the average there. We could increase the value of n. Maybe we don't choose 20 chips. Maybe we choose 100 times. And then we're going to see these values get closer and closer to that 0.4, the true proportion, that population characteristic there. I'll tell you that when I did it before this coming to this meet today, I got 0.425 was my average of my p-hat, so just a little bit over that. So you can see that if I actually take the average of my sample proportions here and I combine it with the 4 trials over there, I'm going to get really, really close to that 0.4, right? So hopefully that all makes sense. All right, last 2 questions, and this is actually all of today's lesson, by the way, is an example 1 here. Simulate 10 flips of a fair coin. Record your steps and observations. What is your sample proportion of tails? Okay, so we have to somehow define what we want heads and tails to be. I think the easiest thing is when we do our random int, let's let 1 equal tails, and we'll let 2 equal heads. We're trying to simulate 10 flips of the fair coin. So we want, in this case, n to equal 10. And we know that the actual population characteristic here is that when you flip a coin, it's going to be a 50-50 chance, right? 0.50 is the population characteristic of getting tails. So really quickly, what we can do is we can do a rand int. So we'll do math, probability, option 5. And what am I going to type into rand int? Well, the lower is 1. The upper is 2. Right? We only want the numbers 1 and 2. And we want to simulate this 10 times. Okay. So if we do rand int, in terms of just writing out some work, I'll write down what we're simulating on the calculator, which is 1, 2, 10. All right, if I hit enter, we're looking at all the number 1s in the list. Now, could I store this in a list? Sure, but I can really easily just count the number 1s up here. So we got 1, 2, 3, 4, 5. Actually, I got the exact value of p just simulating that 10 times. Will that always happen? Probably not. Okay, but my p-hat in this case winds up being 5 out of 10, which is actually that population characteristic. If I were to do that again, I may not get that p-hat to be 0.5 again. Here it's 1, 2, 3, 4, 5. Now it was actually 6 out of 10. Okay, when I did it earlier, it was 4 out of 10. So, if you increase that value of n, the number of times you simulate this, you're going to get closer and closer and closer and closer each time to getting the true population characteristic of 0.5. Okay, and then last but not least, we have one more example. We're talking about green Skittles. Apparently, in a Skittles bag, 10% are green, 90% would not be green. So simulate randomly selecting 20 Skittles, record your steps, and then state your observations. All right, so what would be my steps? Well, we have to somehow define a system that would get me to differentiate between Skittles that are green and Skittles that are not green. So that 10% and 90% split, why don't we say, let's let the number 1 represent a green Skittle, and then we'll do the numbers 2 through 10 would be Skittles that are not green. All right, we know that we're going to do this a total of, we're selecting 20 Skittles, so that's our value of n. We know that the true population characteristic is that there should be 10% of the Skittles are green. So we're going to do rand int. My lower is 1, my upper bound is 10, and we're going to do this 20 times. I'm actually going to store this in list 1 because we have the numbers 1 through 10 and we have 20 of them. So just to kind of make my life a little bit easier, I'll store it in there to write a little bit more work. I then kind of like the idea of sorting that list because I just want to know how many number 1s do I get. So one more time here, go ahead and hit, let's see, so we need math, probability, option 5. The upper now is from 1 to 10. We're going to do this 20 times, paste it. Okay, those are the numbers. We're going to store that in list 1. We're going to stat option 2, sort A for list 1. Okay, and then if I go to stat edit, I have all these other data from before. I'll remind you how to clear that out. But how many number 1s did I get? I got in list 1 just the first 2 are the number 1. So I wound up getting my p hat was 2 out of 20, okay, which happens to be the population characteristic of 0.10. When I did this earlier, I got 3 out of 20. So, again, it wouldn't be a huge deal if we don't get the exact, but the whole idea is that when I increase the sample size, when I increase the number of Skittles that we randomly select, we're going to see that this value gets closer and closer and closer to the true population characteristic. Okay. One other quick note is if you wanted to simplify the process up above, if we know that 40% of the population was red, you didn't have to go 1 through 40, right? I mean, we just did 10%, 90%. I didn't go 1 through 10 and then also, 10 through or 11 through 90. 11 through 100 there, sorry. We can do the same thing up here. For 40%, you can let's say 1 through 4 be red and 5 through 10 be blue or some other color, something like that. So just keep in mind that as you're working through some of these questions, however you define it, as long as it represents the population proportion that's given to you, you should be good to go. But one other quick note is I told you I was going to let you know how to clear out these lists here. Remember that when you go up and highlight L4 or any list in your calculator, you hit the clear button. Do not hit delete because it will delete the list forever. Okay, if you scroll down, now that list is cleared out. Okay, I can do that for L3, hit clear, L2, and then L1, and now I'm ready to rock and type in more data if I need to. Okay, all right, that's it for today. The homework is really fast for this lesson, so let me know if you have any questions, and talk to you guys soon.